Mr. Yannick Willemin. He is head marketing and business development at the 90 Labs. And he talks today about stronger and lighter than metal through additive fusion technology using CFRP. The stage is yours.
Thank you for the introducing words. Dear ladies and gentlemen, it's a pleasure to be here with you in this room. There are a lot of premieres today, so for me it's first time in Hanover ever, and it's also first time for LightCon, so it's great that Thomas and the entire team put that together, had 2 years to work hard and now implement it. And I really like the concept because often those events are very exclusive, so we speak about verticals, we speak about specific materials, metals or composites, or we speak about different industries, aerospace, automotive, and here we speak about a function, so that's really going back to the essence of engineering, really looking at the best out of people, materials, processes to get something new, something better, and probably something more sustainable on the long term. So let me start with presenting the company, 90 Labs, who we are. So we are a Swiss-based company, founded in 2018. It's a spin-off of ETH Zurich. This year, we were super happy to collect or to fundraise 17 million for a Series A in February, and we currently count 51 employees, all based in Zurich, Switzerland, for the time being. So let me quickly introduce why we work on continuous fiber thermoplastics. So those kind of materials, they have outstanding properties in many different ways. So we have a whole tool set of properties we want to use, depending on the application, of course. So of course, lightweight, that's the topic today, but there is other functions you can add to that. Radiolucency for medical is very interesting. Recyclability, obviously, big point for sustainability, and so on. However, we have all these great properties, but still, in terms of processing, especially for smaller, intricate parts, we have very tedious, often manual processes. So that means that metal also remain easier to process, to calculate, easier to forecast what will happen in the future with those metal parts because we have way more experience. And we also currently have a cost issue. So composites, because of this tedious processes, are up to 3 times more expensive for similar parts than the metal. So to kind of break these hurdles, to break these barriers, what we try to do is we work on different pillars because only with converging innovation we can get to the next step and really get rid of those current issues. So we look at the material side, of course. So here it's about continuous fiber materials in general. We tap into the thermoplastics because they are very interesting for us for different reasons, sustainability being one of them, also the speed of processing. And here it's about performance, about using industry standard materials, so off-the-shelf materials, so that customers don't need to re-qualify and get used to a new class of self-developed materials. And last but not least, they need to be cost competitive. Then, when printing or when processing, we are looking at a process which is allowing us to place the material in a very granular way. So we want fibers where we need reinforcement, but we want pure plastic, for example, where we don't need reinforcement to also be more efficient. And we also want to be near to end shape. So 3D printing is really fulfilling this, at least on the preform side, but we don't have the final properties. That's when we add a molding step, so post-consolidation, to really get all the final properties expected for serial parts in structural applications. So it means high reproducibility, repeatability, low porosity, and very good tolerances. Of course, this is a seamless process. So there's a lot of interaction of the software. So it's about designing parts for this type of manufacturing, but also for the end use case, combining this design and validated the geometries with the right materials, sending it to a process, in this case, a 3D printing process, to, in a very automated way, put the material where it needs to be, and finally get the properties out of these preforms up to the end part. Just a reminder of the properties, or one property, the tensile strength of those materials. So on the left side, the two red bars show continuous carbon fiber with PEC, or continuous carbon fiber with PA12, in comparison with some metals like steel, aluminum, titanium. So we see there is a huge difference in performance. Of course, it's also sometimes about the combination of metals and composites, depending on the final functions you need in the part. And now I would like to explain how we go through our process with a clear, easy to understand example, which is a human exoskeleton, at least a part of it. And here the challenge was brought by a composite center, CDCQ in Quebec, and Mawashi, an exoskeleton building company. So here it's about having an exoskeleton which is light, which is of course strong to support the loads, here in this case the backpack. However, you also need to keep agility for the people who are carrying those loads. You don't want to hinder them in the movement. And it needs to be serial parts capable. So we need to produce more than just a prototype. So that's a cost topic. In terms of processes and material needs, we have, of course, a need of digital designing tools, validation, so that we can make sure that what we produce afterward is going to sustain the loads. We wanted something very material efficient, so net shape production, and at the end, of course, using high performance materials which will sustain the loads over a longer time. So this winglet, that's how we call it, is really the first part which touches the backpack and where the loads are then transferred into the entire exoskeleton up to the legs. So it has a complex shape, double curved, and is currently made out of printed titanium. So that's the benchmark. This is just a workflow. I will go into the individual steps afterwards, but you see that we design the part first, we validate it, send it to the build module as a code. Then out of the build module, we get some preforms. Those preforms are then put into a mold, co-consolidated, reshaped, and we get the final double curved part out of this. So first step, obviously, is designing. So it's how to lay down the fibers for the loads, but also for the process. And here we iterate very quickly between design and simulation. So we simulate here the rigidity of the parts, the deflection. And as long as we couldn't validate the expected deflection, we were just looping from design to simulation. Once we have found an optimal design, we created the G-code, send it to the printer. Out of the printer on the left side, you see those 9 subparts. Why they are 9? Actually, that's interesting because we print plain, so it's a flat part, but we need to put it into a mold which is shaped, so the surface is smaller in the mold, and we need some flexibility to put those parts into the mold. However, during the molding process, the bonding between the layers and the different parts is going to be excellent, so it's not a big deal to have 9 parts which will end up being one single homogeneous part with a double curved structure, as you see on the right side. Finally, of course, we need to demonstrate that the part is fulfilling the request in terms of deflection, rigidity. We used here digital image measurements, and we could prove that we are on par with the titanium parts and below what is required either way by the manufacturer. In terms of results, so on the lightweight topic, we are able to be more than half of the weight. So that's very interesting. And we are also cost competitive. Of course, note that 3D printing titanium is very expensive. However, we can also show that in this application, we can cut the costs by 75%. So the outlook is currently the exoskeleton weighs 7 kilograms, is made out of 20 parts, and the goal is to have lighter exoskeleton by 50%, and that's where we are coming into the development of the next generation. So some learnings here. Obviously, our process is capable to do net shape preforms. We can also show that the digital design workflow works well because we could validate this with real measurement, real tests at the end. We have also demonstrated that there is a significant weight saving, 50%, a bit more even, and that we can produce it in many parts, so we can go into volume production. So beyond this example, what we are looking at with our technology are various parts. Of course, they are limited in size because of the print volume for now, but we look into aerospace. On the top right, you see helicopter door hinge, so all brackets, connectors, highly loaded parts are of interest. In the medical field, it's a combination of the radiolucency function and also the resistance to dilatation through the continuous fibers. So you see medical instruments on the bottom right, very interesting application for us. Automotive is a topic also, and luxury and sports, because we can access those markets way faster because they are not regulated, obviously. So you see an example of a watch case here on the bottom left. We work also on rocker arms for mountain bikes, for example. So here it's really about finding the right use cases, the right business cases. And feel free to visit us downstairs on B24. We have a lot of demonstrators, you can touch them. Thank you again for your attention.
Thank you for the presentation. This was very fast, perfect. We are in time. Yeah, do you have any question to Mr. Willemin? No, I think maybe I have a question to you. You showed, I think on your second slide, a bubble with recyclable or recycling with this word. Could you explain something about the recycling? Is it possible, this material and use? Is there a process behind or?
Sure. Yeah, I mean, thermoplastics obviously are a bit easier to recycle. The challenge is always how to separate fibers from the matrix. And of course, you cannot pull out the continuous fibers and reuse it as such, but you could chop the fibers and then reuse them as chips. So what we do more and more is also combining very precisely 3D printed parts where it's necessary, and then filling the remaining of the volume with recycled chips, for example. That's a possibility. Idea, yes. We have an example downstairs of a part we are doing with a university. So it's really how to reuse also and how to maximize the efficiency of the process.
Okay, thank you. If you have a question, maybe use the microphone or on the right side.
Just to tap on that, how about different materials that are lend themselves better for recycling or reuse other than carbon fiber?
Yeah, so I mean, of course, there is a matrix side, so we can speak about recyclable or biosourced polymers, but also on the fiber side, of course, we can go into other continuous fibers. So whatever, we also use basalt fiber sometimes, which is one example of biosource fibers. We hear a lot of about flax fibers, but then it depends also on the temperatures you want to, to treat the part afterwards. But yeah, all of them are very important, especially for those leisure markets, because there it's also a selling argument for the end consumers. Thank you.
Thank you.
Okay. Any other question? It's okay. Thank you so much again,
Thank you.
Mr. Willemin. Yeah, also applause.